All right, folks, let's start. This is Dr. Yuzo, ECE 341, our system class. Can you guys hear me? All right, thank you guys. And so let's go ahead. So this is my notes. First one is an example. The second example for power flow calculation. And please copy this problem. And after this example, we are done with this module. Okay. We will have a quiz opened right after the end of today's lecture and due in 24 hours from then. And another 1 day long quiz. Okay, and don't forget to do it. Okay, this is the quiz. And also today we are going to talk about our project. Okay, the project is going to be open today as well. Okay, due in 4 weeks, if I remember it correctly. Okay, so this is the second thing for today's lecture. The last thing today is continue our review of the midterm 1 to finish the rest of the three problems. Okay. For this power flow example 2, okay, I'm also placing the formula. Okay, the formula here as a review. To calculate line flow, you need to calculate the pair for each line, and it equals to the voltage times the current conjugate. Very straightforward. The current could be equals to the voltage potential difference times the admittance or divided by the impedance. Okay, either way works. And line loss is equals to the line flows sum along the same line. The bus flow means, I'm sorry, bus power. Bus power means the total line flows summation. Okay. So these are very basic equations, and apply which, please go ahead to try to do this problem. Well, as you can see in this problem, no bus voltages are given, no line impedance or admittances are given either. However, all of the line flows are given. All of the line flows are given, right? So you don't need to calculate any line flows. Instead, you're trying to find line losses and bus powers based on the given line flows. It's doable. If everything makes sense to you, you should be able to do this. And then also try to label them all into the given network diagram. Okay. All right, go ahead. So a little bit hint here. So from line flows, you can easily find line loss, right? So we have 3 line loss. And also we have 3 bus power. And how to find bus power? We have just so this formula. Okay, to sum all of the power starting from the bus. That is nothing but the bus power. In other words, the left-hand side of the bus power equals to the right-hand side summation of all of the line flows. So find them and label them all into the network. Okay. Give you guys 10 minutes should be more than enough. Go ahead. Then we will come back to see. Okay. Try to do this exercise. Okay. If anything you need to review, you can open your notes to see what you have done in example 1. All right, let's take a look at the solution here. I think it's very straightforward. First of all, we can find the line loss, right? Based on line flows S12 and S21, easily line loss between bus 1 and bus 2, labeled as S sub L12, equals to the sum of 2. Right? And just the equals to right? Be very careful with the unit, okay? It's not SI unit, not yet. Just the per unit. We keep per unit, that's fine. And just remember, you need to find the actual value based on the given base power value so that you can label them into the graph. Okay. The line loss first. Second line loss. This is the 1, 3, not 3, 1. Okay. I'm sorry. This the result is actually I have converted to the SI unit. Yes. This 8.4 and 16.2 already the SI unit. I already times 100. Okay, which is the base power. So this is the line loss. This is also the SI unit, 0.8183 plus 0.449J. And similarly, we have the line loss between bus 2 and 3. Once again, it's in mega VA. Okay. I have already times on the base power value. Okay. This is the line loss. If you label them, actually you can do labeling like this, right? Line loss is right in the middle of the line. So between bus 1 and bus 2, you have this guy. So 8.4 on top, 16.2 in the bottom, given parentheses to contain them. By writing them in this way, you are basically assuming above the line is active power, below it is the reactive power. Okay, so keep this consistent when you label the line flows. The second, between bus 1 and 3, you have loss and right. And once again, in this way, you are pretty much setting up the location for say the side of active and reactive power. Okay. This is 2, 3. Three line loss.
Can't we denote the complex part with a J, or does it have to be left?
No, no J. No J. No J here. Of course, if you label it J, theoretically is not wrong. I agree with that. But the reason we don't have to label J is by the side, you can tell this is active or reactive. That's why we are not involving the J. This kind of a rule when you plot or label a per phase power system network. But theoretically, I don't think that is wrong, of course. All right, before labeling, we can now either start to label the line flows, or we can find the bus power first, right? So we can find bus power first. First bus power, say, is S1, right? Second will be S2. Third one will be S3. So how to find S1? S1 is obviously here, right? It's here, the power on this side. Obviously, it equals the sum of the power here and here, right? The power, sum of power here and here, they're respectively what? S12 and S13. Does it make sense? Similarly, the bus power for bus 2 means this side, this end, equals to the summation of power here and the power here, right? They are respectively S21 and S23, right? Similarly, the S3 equals to S31 plus S32. S12, 13, you sum them up, and then you end up with, well, the digits is a little bit too many. You can just use 2 digits here and to use 2 digits here, and that's fair. End up with the 2.18 as active power and in per unit, and 1, 2 reactive, and 1, 3 reactive. Okay. This place is a little bit too small. And 2, 1, 2, 3. 2, 1, 2, 3, basically. Let me label this. Let's make it even. So this guy go here. This guy go here too, right? Now to S2, you have this guy who go here. And this guy go here, right? So here, plus here, what do you got? Basically got the negative 3.999. Right? And negative here is 2.5. Okay, per unit. And 3.1 is here. 3.2 is here. This two. Right. So this is how we find all of the line flows. Of course, they're given, and line loss and bus power. And then to label them into the graph, we can begin with S12. S12. First of all, the location is here. Okay, this is a very important. S12 means close to bus 1, and is a positive 1.979. So it's this way. Reactive power is also positive. Okay, it's this way, but with a bar with it, indicating the reactive power. So active power is equals to what? Don't forget the base power, 100. So is 179, right? And the reactive power is 118.8. And then we can go ahead to label the S21. S21 location is here. 2, 1, look at the order. So it basically means from 2 towards 1. It's supposed to be towards left arrow. However, the values are negative and the negative for active and reactive power, both. So we flipped direction. And then therefore we are labeling with positive value, right? 179.9 as the active power. And 102 as the reactive power. And then 13 is here. 13 is here. Active is positive and positive. Above the line here is supposed to be active power because you have labeled the active power loss here on this side, right? So be careful. Once again, it must be consistent. So the positive here is 39.061. 22.118, right? And once again, don't forget to times the base power. And 31 is here. 31, the location is here. Negative and negative. Okay, we flip the direction this way. And then label the positive value. 38.878. 21.569. And the next, the 2, 3, negative and the negative, be careful. 2, 3 means from 2 towards 3. However, it's negative value. So we flipped arrow direction. Once again, be careful. Above the line is active power loss. Below it is reactive power loss. So above the line, this is active power line flow. Below it is reactive line flow. So 2, 3 is here, 229.032. Reactive is 148.053. The last one is 32 from 3 to towards 2. Okay, positive. Okay. So left is active. Left above it is active. Right, this one is reactive, and below this line is reactive. They're consistent. Always along the same line, same side. Okay. Always along the same side. Active this time is 3238 167.878. Reactive is 167.746. Right. So take a look to see any questions. So this problem is pretty much telling us, this example pretty much telling us that a given line flow, we can find anything else, and also we should be able to label them into the graph. Here I'm receiving a question. Jacob is asking, so you must find line loss before bus power? No, not necessary. Not necessary. You can do any way you want. Okay. And say if you have the line flows, you find the bus power first. That's absolutely fine. That's absolutely fine. Order doesn't matter. Absolutely fine.
So the circle is denoting a source. Is that what is
correct?
To be there?
Correct. This is a generator.
It just seems weird that node 1 appears to be supplying power to the generator, or is that?
Hold on. John pretty much is reminding us we haven't yet labeled line the bus power, right? We need to do that. Okay, label S1, 2, 3 into the graph as well. Okay, don't forget to do that. So first S1 is this. So look at the right-hand side of the bus 1. They're all towards right? So this side is, you don't need to think, it's definitely this way. Otherwise, it makes no sense. And the value is obviously here 218 and then 140.9. S2, left-hand side of the S2 are all towards right. So is the right-hand side of bus 2. So it's actually 3.999 as active, 250. Okay, this is not 3.99. We need to times 100, so 399.9. Reactive power is 250. Bus 3 is positive 200 and positive 146.2. But by looking here, it basically is providing these amount of 200 something and also receiving certain active power. Okay? So the total active power is still providing to the rest of the network, which is 200. Reactive power, following the similar idea, is also providing 146.2. Does it make sense?
Why wouldn't they say that there's some sort of generator going on the node 1 if it's providing some sort of power?
This is actually part of the network. And here, well, there's something here is providing power to it. There's a source before it, providing power to it. Does it make sense?
And so they,
if it's the load, no, then obviously it won't provide the active power.
So it's some sort of generator as well, or is it not?
Yes, before it, yes.
So there should be a circle and a line then going into node 1.
Or you have a third of connection to another source.
Oh, okay. So maybe that's like that's a sub circuit or something like that.
Yes,
Somewhere on it.
yes,
Okay.
yes, yes, yes.
Gotcha.
Yep. I mean, here is another pair of line flows providing power to it. So at any bus, you can see the left and the right hand side of it power what conservation, right? So that makes perfect sense. And of course, it's also possible, like Joe mentioned, this is a source power by itself. That makes sense too. Right. Point zero. Oh, here there's a little calculation small error when you calculate the loss here. I think the pointed out by Anil. And actually, this is because actually I'm calculating this problem based on the given bus voltage. So from there, I have different number of digits after the dot. So when you do this calculation, it's going to be a little bit different. Any other questions? Because this is power when you calculate the per unit value at the first place. Now you probably have certain amount of digits. After times 100, which is the base power, you gotta rounding, do some rounding. Once you do some rounding, and then the digits, the power value, gonna be a little bit different. But if you got 0.8, not 0.8, 0.084 or 0.8081, because that's the per unit value, right? 0.08 or 4 or 0.081, that doesn't matter, actually. It won't change too much.
So if each one of the lines was three phase, we would just literally multiply the whole circuit by three.
In this per unit, because this given network is per phase, right? It's per phase, not per unit, it's per phase, right? It's per phase, then you label everything per phase as well. Of course, you keep in mind that it's supposed to be three-phase system, and so the power value is supposed to be triple. However, the given graph network here is per phase circuit. You can't label three-phase power into it. Right?
But I mean, if you wanted to know the total line power consumed, you would multiply that by 3, wouldn't you? 8.
Yes, yes, yes.
Okay. So then would the problem tell us that it needs to be a single or a per phase power diagram? Or power diagram?
Yes, per phase.
Would it ever say three phase or
No. The network diagram is, generally speaking, always per phase.
And if the impedances aren't exactly the same, then you would basically need 3 per phase circuits.
Yes, that's why it's balanced. Balance the three phase network.
Okay.
Any other questions, concerns? And from the quiz, you will see actually the quiz. What happened in the quiz is I labeled or say giving you and labeling some of the line flows and line loss and loss powers. Some of them. Ask you to find the rest. Ask you to find the rest based on the givens. So if you can understand very well the relationship among them, then probably you don't have to do the V times I conjugate for all of the missing line flows. You don't have to do that for all of them. For example, given this S12 and line loss S12, you can easily find the S21, right? You don't have to use V2 times I12 conjugate. Does it make sense? All right. Any more questions?